So we start with this. So one of the principles that I think you have learned, come across, is principle of minimum strain energy, which is given by these equations, where you, for this particular example, you differentiate the strain energy, which is expressed as a function of displacement, is equal to the force applied at the same point as the displacement and in the same directions. So this can also be, the displacement here can also be rotations, and the corresponding force here will be moment. Okay. So this is one of the principles that we frequently use to solve structural mechanics problem instead of using the equilibrium approach. So we don't use any equilibrium equation here, but finally we can solve for delta. Okay. Another principle that I briefly touched with you is principle of virtual work. This is a very powerful principle. Okay. The principle of virtual work states that, I think, if a structure which is in equilibrium, this structure which is in equilibrium, and if you disturb it, if you disturb this by giving it a virtual displacement, so this structure, when you apply load, the spring will become shortened. And when it comes here, it is in equilibrium. And at this equilibrium state, if you disturb this by a virtual displacement, here we use this delta to represent virtual. Yeah, virtual. Then, because you disturb this, there's a load applied here. There is a work done by this load that we apply. This is a real load that we apply, external load. So from the definition of work done, which is the product of P multiplied with delta. So here we have delta that we use to represent virtual, okay, which is not real. This is not real. Okay. So the work done by external, this is external load because this is applied one. So that's why we put external here. And we use this because this is work done by the real load, because this one is given a virtual displacement. So this is also external virtual work. Then correspondingly, we have internal virtual work. Internal virtual work is done by the internal force. In this spring, because this load applied, so this spring is compressed. So there is internal force in the spring. So from the spring constant K, we know that for material properties from the spring, internal force is equal to K multiplied with how much shortening it has. So you have an internal force which is acting opposite to P. And this internal force also will do some work. And the work done is negative K delta, delta, delta. Why negative K? Why negative? Because the directions of the internal force and the direction of this is opposite. That's why we have a negative here. This we don't have negative because this direction and this direction is the same. So there's no negative. But here there is a negative because internal force is acting like this, but the virtual displacement is, you give virtual displacement is in this direction, then you have a negative here. So the principle of virtual work, basically it says that for structural system in equilibrium, so pay attention to these words here. So for a structural system in equilibrium, in this case, you apply the force P, this one shortened by delta. So in that state, it is in equilibrium. Then the sum of external and internal virtual work, if you sum this up together, it is 0. Okay. So this is the definitions of principle of virtual displacement. So what is the use of this principle? We apply this principle to derive equilibrium equations. We apply the principle of virtual displacement to derive equilibrium equations. So this is another way to get equilibrium equations. The normal way that we are familiar with is internal force equal to external force. That is equilibrium. So another way, we can use principle of virtual displacement to define equilibrium. Okay? So this is statement of equilibrium. So if you substitute this and this here, okay, if you substitute this and that there, what you are going to get? You are going to get the solution for delta, for the equilibrium equations. Okay. Now I'm going to move to okay. This is not connected. So if you try to substitute this delta W external and delta W internal, what you are going to get is you are going to get an equation. And that equation is the equilibrium equation that you can solve. Now let me substitute this delta W external and delta W internal into that expression and see what you get. Let me use the plot here. So class, we're online now. I'm going to use the whiteboard now. So now hopefully you can see me, yeah? Okay. Now if we apply principle of virtual displacement, so this is representing virtual. This is virtual work internal and virtual work external, and they must be equal to 0 according to principle of virtual work. So this one is P delta delta. Then internal work is negative K delta delta delta. This is equal to 0. So we can then take this minus K delta, go to this. So here, this multiplied with this, and this is virtual displacement. So for this to be valid, this multiplied to be equal to 0, and this can be any value. So this must be equal to 0. Okay. So from here, you get P is equal to K delta, which means the equilibrium equations. External force equal to internal force. So by applying principle of virtual displacement, you get equilibrium equations. And from here, you can solve for delta. So here, delta is equal to P over K. Okay. So this is a simple example of applying it to a very simple spring. So simple spring, of course, you don't need to use this, but we can use this, then we can prove that we can finally get this equation, which is an equilibrium equations. External force equal to internal force. Okay. So that is the power of principle of virtual displacement. So now if we now later we will come back again to principle of virtual displacement and how actually it can give us the principle that we want to derive in order to solve the problem. So we are going to, in this EAS661, in the 4 weeks, including this week, starting this week, we will look at this starting with principle of virtual displacement. Okay. Then we will go to specializations. So principle of virtual displacement is a general, just like 3D elasticity, then you can specialize. So from principle of virtual displacement, we can specialize it to a class of a specific type of problem that we want to solve. And we specialize that to principle of minimum potential energy that we call the short form PMPE. Here the short form we call principle of virtual displacement. Then in order to solve problems, then we have a method that we call Rayleigh-Ritz method, which is a method where it makes use of principle of energy to solve the problem. So we will see Rayleigh-Ritz method. This is a very common method for solving. Then we go next to piecewise Rayleigh-Ritz, where we divide the problem that we want to solve. We divide the structure into parts, and each part we consider we apply principle. We apply Rayleigh-Ritz method. Okay. So this piecewise Rayleigh-Ritz method is finally extended to finite element method. Okay. So these are the flow that we want to go through. So these things is what I will cover. I will cover until here. Then Rayleigh-Ritz method, I think Dr. Mustafa Sani will take over to go through with you the Rayleigh-Ritz method. I will cover the basic, and then he will cover the Rayleigh-Ritz method and its applications. Now, in order to apply principle of energy, we need to evaluate strain energy of structures. So in this lecture, we are going to look at mainly 1D problems, okay, but it can be extended to 2D problem later. We will just mention how you can apply it to 2D or 3D problems. So we will specifically look at application of energy method to solve 1D problem, the principle behind, and to solve problems using energy method, we need to know how to get the strain energy. Strain energy is, you can understand as something which is stored in the structure when it is deformed. So basically, we have 3 main types of deformations, which is axial deformations. Then you get strain energy because a bar is being, you pull it longer or you push it shorter, you have energy stored in the bar. Then the other basic deformation is twisting. When you twist a bar, then you have energy stored in the bar. Okay. Flexually loaded, if you bend a beam, if you bend it, then you have energy stored in the beam as well. So this energy is stored, and when you let go, this energy will do work and this bar will go back to the original shape. So we will have to look at what is the strain energy equations for the case of axial deformations, for the case of twisting deformation, and for the case of bending deformations. Okay. Now, this is the first, okay, the first thing that we would like to look at. Basic idea about work and strain energy. I think this thing you have already studied before. We have to get this idea again refreshed so that later when we go to principle of energy, we can apply these basic definitions. So work and strain energy. Okay. Here we are using again the case of axially loaded bar, a very simple axially loaded bar. We have a bar which is, you have seen this many times now, fixed here, okay, and it is pulled by another force at the other end there. Okay, and this is the axis x direction of the bar. And when the bar is being pulled, then the bar is getting longer until when you reach a certain force, then the elongation is E there. Okay. So if we try to plot a graph showing what happened between the force and the elongation, and also because when you pull the bar, you have stresses develop, you have axial stress develop. When we plot another graph here, which is the stresses developed in the bar versus the strain developed, the strain that happened in the bar. So these are two diagrams here. Okay. The first one is the force versus elongation. So this might be Newton mm or kilonewton meter. Okay. And the second one is stress versus strain. This might be Newton per meter square. This has no unit. So these are two different plots. Okay. This we use to represent what happened to the bar. Okay. We look at the first one first in diagram B. Yeah. You look at this one first in diagram B. The one online, suddenly you don't see me, don't worry. I will once in a while appear in front of this camera so that you can see me. I'm still here, okay? Suddenly you don't see me, and then you, but I hope you can hear me, okay? So what I want you to understand is the definition of work done, okay? Definition of work. So here we have the force slowly applied from zero. The force starting from zero. Then you slowly increase the magnitude of the force. Then elongation also will start to increase. Start from zero, no elongation, and then slowly elongation increase. So until you pull it to certain elongation and the force is equal to F, then you stop there. So generally the relations will be non-linear. Generally the relation will be non-linear. Okay. Then same thing, if you have a force, then you divide it by the area, you get axial stress. So the axial stress also starts from zero. And if you have a elongation, you divide it by original length, then you get the strain. The strain also will slowly develop as the force is applied. You develop the stress. So the relationship is given by this curve here. Also, it is generally non-linear. Generally non-linear. Okay. So this is represent the general case where the material can be non-linear. But later, when we restrict our problem to linear, so this becomes straight line. This becomes a straight line. Okay. So what I would like you to pay attention is the area under the graph here. Area under the graph here. This is area under force elongation. This is area under stress strain. Okay. So now, if we look at a particular instance, yeah, we look at a particular instance where the force that you slowly apply, the force that you slowly apply is magnitude is Fs. This is intermediate state, and the corresponding elongation at that time is ES. Okay, so this is a particular state. So then, if we increase this a little bit, elongation, if you increase this force a little bit, dF, and the corresponding elongation is DES, okay? Then if you combine everything, all these things together, you combine all this area together, this small area, yeah, this area, you combine them together, you get area under the graph. The same thing here, if your force is at intermediate value, so the stress is also intermediate value at sigma x is equal to S, okay? At sigma x is equal to S. Then at that particular state, if we increase the force a small value, you get a small stress increase and the correspondingly a small strain increase. So during this small increment, we have a small increment here. If you add up all these small increment, then you get the area under the graph here. Okay. So the area under the graph that I show you just now, yeah, this area under the graph, this represents the work done by the externally applied force. This area under this graph, force versus elongations here, gives you the work done by the externally applied force, F. And the corresponding area under this graph here, stress versus strain, give you the strain energy density. It gives you the strain energy density. Okay. So remember, area under force versus elongation is equivalent to work done by the force, and the corresponding area under the corresponding stress. Axial stress here with axial strain is the strain energy density. Okay? Strain energy density. So because the area under the graph is equal to the work done, so the equation representing the work done is given by this first equation here. By this equation here. So work done by the external force, Fs, F is equal to integrations from 0 to the final elongation E, and this Fs multiplied with DES, that is a work done. And when you have a work done by the force, the member become longer, then you have energy store. You have an energy store in the member, and that energy is called strain energy. That energy is called strain energy, and that strain energy is equal to the work done. So strain energy is equal to work done by the force. It is stored in the structure. This equation and this equation is valid for conservative and elastic system. Okay? Conservative means the loading does not depend on how you apply the sequence. Okay? It only depends on the final state. And elastic means the member still, if you pull it, it elongates. If you let go, it goes back to the original shape. So this is the first thing that I want you to understand. I think refresh. So the work done in general is given by that expression, is area under the curve just now. And the work done for elastic and conservative system is equal to strain energy. Okay. And we use the symbol U, capital and subscript P for strain energy in our lectures. Okay. And strain energy also is called potential energy of deformations. Strain energy happens because we have deformations. So it is also called potential energy of deformations. Okay. Now, if there is external work, W subscript E, there is also internal work. Okay. Internal work is a work done by the internal force. When you pull the bar getting longer, then the internal force develops. The internal force also is doing some work. But because the internal force is acting in opposite directions to the deformations, so we have this relationship. The strain energy, which is equal to the external work, is equal to negative of internal work. This one must be a positive value. This Wi internal work is negative because the internal force is acting opposite direction to deformations. So this is a negative value. So for this to become positive, we must put a negative here. So this is another relationship that I want you to keep in mind. Strain energy is equal to negative of internal work. Okay. Strain energy is equal to negative of internal work. So the first one, definition of work done is given by this. This is area under the force versus deformation diagram. Then for conservative and elastic system, the work done by external force is equal to strain energy. And strain energy is equal to negative of internal work. So these three basic relations is the one that we are going to use. So you have to remember this. Yes. Again? Which one? Which one? Oh, yeah. Work done. Yeah. Yes. Work done by the external load. Yeah. Okay. This is the work done by the external load. Because we have work done is because we have a load applied. So this is the work done by the external load. And this is if you this definition, this integration means is area under the curve. So F is this, F is this, F ds is this area. So if you add up all this small area, then you get this total area. You add up this small area, meaning you integrate from 0 to E. Okay. And you get the area under the curve. So this is why we call this work done by the externally applied force. So your question is work done by the externally applied force. Okay. So now we want to make use of these definitions and try to derive this. First, we look at axially loaded bars. The equation will become like this. Then we go through the similar process. We go to bending of beams. So the equation will be like this. And next is twisting. The twisting, the equation will be like this. So these are the basic equation for strain energy for axial deformation. This is for bending deformation, and this is for twisting. And here we have cross-sectional area A. This one is elastic modulus E, AE, and then you have E the same. I is the moment inertia. G is shear modulus. J is torsional constant. So U is axial deformations. V is later in bending, we have the vertical deflections of beam. And theta is angle of twist. Theta is angle of twist as I shown in that diagram there. So these are the equations that you need to know and which will be applied later in the energy method to solve the problem. Okay. So when do we need to use this? When do you need to use this? When do you need to use this? If you look at the problem, if the loading causes axial deformations, does the loading also cause bending? Does the loading cause twisting? If all this happen, then you have to add up all this. Okay. So that is the one that we want to look at. Okay. Before that, let me go to, after I go through this, then I will go to this. I come back to how to derive this. So I will go to this principle of virtual displacement. Okay. Principle of virtual displacement is a very powerful principle that we can use to solve a problem because it gives us the alternative way of defining equilibrium. Now, this one is to prove that. Now, principle of virtual displacement says that if the structure or the system is in equilibrium under the action of certain set of external load, then the virtual work done by all the load applied on that system, if you give that system a virtual displacement, the virtual work done will be equal to 0. So this is to prove that statement. So here we are using a particle. Okay? We are using a particle. So here we show a particle P, which is acted by a system of forces. So the force is represented by this arrow here. So we have a forces F1, F2, F3, F4 until F. It can be any numbers of force applied on that particle, and all this particle is making some angle, with certain reference line. All this external load is making some angle with certain external line that we reference from here. The reference can be here, can be any. What we reference, this is the reference to measure what is the inclination of that applied force. Okay? These are the applied force. Okay? So this one is in equilibrium. This one is in equilibrium, okay? Which means the summation of the forces in this direction, in another direction, on any direction, 0. This is in equilibrium. Okay? So now, principle of virtual displacement, the idea behind the principle of virtual displacement, that when the system is in equilibrium, then you try to disturb it. You try to disturb it. Here, we disturb it by giving it a virtual displacement. You disturb the system. So you disturb the system in these directions by a displacement that we call virtual. So here in these lectures here on energy method, delta represent virtual. Okay. So virtual displacement A in certain directions this. Okay. Then, according to definition of work, there is a system of forces applied, and if this system, because it's applied on this particle, but this particle moves in this direction, delta A, so there is a work done by all these forces here. So the work done is defined as the product of the force in the direction of this red line here, multiplied with the corresponding displacement. Okay. So that is a definition of work. So the definition of work, by applying the definition of work, so the virtual work equations is represented by this equation here. So again, class, this is virtual work. Now, virtual work here done by the force is equal to, from definition of work, is the products of the force in the same directions of the movement here, multiplied with this, how much it has moved. Okay. But you have to consider positive or negative if they are in different directions. So for example, this force, the work done by this force is F1 cos theta in this direction multiplied with this. They are in the same direction, that's positive. Next, if there's angle here is theta 2, so the work done by this is F2 cos theta 2 multiplied with this, and you do the rest for all the force. And that one you can write very nicely in this very compact way. The same energy, no need to write very long. You put it in a very compact way, given by these equations here, but multiplied with delta A. Okay. So this is the virtual work done by all the forces when this particle is giving virtual displacement in these directions. So this direction can be anywhere. Okay. Now, remember, this particle is in equilibrium. This particle is in equilibrium under the action of these forces. So if the particle is in equilibrium under the action of these forces, then this one is this one meaning the summation of forces, the summation of forces in these directions. So if the structure is in equilibrium, your summation of force in any direction is equal to 0. So this red one, the one that is surrounded by this dotted red square is 0. So if that is 0, then you multiply this, you get 0. Okay. So from here, we prove that if the particle is in equilibrium, then the virtual work done by the external force, by the force applied when the particle is being given a virtual displacement will be 0. Okay. So we come to this statement here. So this statement is representing principle of virtual displacement, and we prove using this simple example. Okay. So here, okay, this is PVD. Okay. If a particle is in equilibrium, we concentrate particle first. If a particle is in equilibrium under a system of real forces, the force is a real one, okay? Then the virtual work done by the real forces when the particle is given virtual displacement is equal to 0. This one can be also, this one is we start with if the particle is in equilibrium, then this is 0. It can also be the other way around, okay? If this is 0, we can prove that if this is 0, then the particle is in equilibrium under a system of real forces. So it can go either way. If a particle is in equilibrium, this must be 0. If this is 0, then the particle is in equilibrium. So either way. Okay. Then this is the two alternative statements, how we define PVD for particle. We start with particle because it's easy to get the equations. Later we extend to not particle, to a structure, to a deformable body. So the one highlighted in yellow here, class, is the power of PVD. So the principle of virtual displacement is an alternative statement to the conditions of equilibrium. What does it mean is equilibrium, normally the classical definition is internal force equal to external force. That is equilibrium. That is equilibrium. Internal force equal to external force, or applied moment equal to resistant moment. That is the classical definition of equilibrium. But under structural mechanics, we can have another way of representing equilibrium, which is by using principle of virtual displacement. Why? Because if the particle is in equilibrium, then this one becomes 0. Or if this is 0, then the particle is in equilibrium. So that is what principle of virtual displacement is used for. We represent equilibrium. Okay. So now if we extend it, just now we start with particle. Yeah? We start with particle, but now we extend principle of virtual displacement to deformable body. Deformable body has many, we can consider deformable body as many particles stay together. And between the particle, there are some spring holding them together, so they form a deformable body. So if you extend that kind of idea, then the principle of virtual displacement will be represented by this equation. Now we have internal virtual work and external virtual work now, because we have internal force and external force. In particle, we don't have, we have only one forces, we don't have internal one, but when there are many particles together forming a deformable body, then the principle of virtual displacement will have two parts like this. So the statement there, a deformable body is in equilibrium. It's not particle anymore, we substitute with deformable body if the total work done by all the external forces plus the total work done by all the internal forces, okay, during any kinematically admissible virtual displacement is 0. So this statement is represented nicely by this equation here. Now, there is a term here, kinematically admissible, which is important later when we look at energy method. So kinematically admissible is the virtual displacement that we give must satisfy certain conditions. What are the conditions? Is the virtual displacement that we apply to the system must be such that it maintains continuity. You cannot have, if the bodies stay together, after you apply virtual displacement, then the body must stay together. Maintain continuity between all parts of the structure, and is also compatible with the kinematic or geometric constraint, which means it must satisfy the kinematic boundary conditions. So that is the conditions that we have to impose on the virtual displacement. So this is the meaning of kinematically admissible. So these terms later will appear again when we apply the principle of minimum potential energy together with Rayleigh-Ritz method to solve problems. So that we will come back to these terms again. But since it's appear here, so understand like kinematically admissible means the virtual displacement that we apply must make sure that all the body must stay in one piece and the geometric boundary condition is satisfied. So the point which cannot move, when you apply virtual displacement, the point must stay there, it cannot move. So that is the meaning of kinematically admissible. So later, as I mentioned, when we use PNPE to solve problems, then we will see how do we check for this requirement. So class, this is an explanation about principle of virtual displacement. Now, if we try to apply principle of virtual displacement to this problem here, okay? Try to apply it to this problem here. Now we know that the equilibrium equation is this. We know the equilibrium equation is this. Okay? We take the equilibrium of this joint in x directions. So the total, all the forces in x direction due to the internal forces, axial force of the member must be equal to externally applied force, and the same thing for y directions. Now we try to get this by using PVD. We try to get this equation by using principle of virtual displacement. This one we can derive by applying the classical definitions of equilibrium. We find the equilibrium of forces in this direction, you get the first equation. You find the equilibrium of forces in y directions, you get the second equilibrium equations. So we don't want to do this here. We do this by applying principle of virtual displacement. Okay? So that is the one that we want to use. We want to try to derive this to show the application of principle of virtual displacement to get these two equations. Okay? So we will take, after you come back, then I show you how to get this. We take a short break. Okay. So then after come back, okay, after 5 minus 60, 300 seconds or so, then we will start this. So class, we will take a short break, then I continue again. Those are online, you can follow clearly, okay? Yeah. Thank you, madam.